So good morning students, we come to the phi function, that is the Euler's phi function after the Mobius function. So it is defined as the number of positive integer less than or equal to m that are relatively prime to m. By relatively prime to m means the GCD of those integer less than or equal to m with m must be equal to 1. So for example, you take m is equal to 7, we have phi of 7 is the number of positive integers less than or equal to 7 that are relatively prime to 7, means all those integers, that is 1, 2, 3, 4, 5, 6, they are less than equal to 7, and their GCD with 7 must be equal to 1. So as we know that 7 is a prime number, so the GCD of any integers, positive integers less than or equal to 7 will be always equal to 1. For example, the GCD of 1 is 7 equal to 1, the GCD of 2 is 7 equal to 1. So therefore, how many of those positive integers less than equal to 7, their GCD is with 7 is equal to 1? There are 6 of them. So we have phi of 7 is equal to 6 because 1, 2, 3, 4, 5, 6. Now take the case m is equal to 6. What is phi of 6? It is the number of positive integers less than equal to 6 that are relatively prime to 6. And what are those integers less than equal to 6? 1, 2, 3, 4, 5, 6. So 6, the GCD of 6 with 6 will be 1. So we'll rule out this 6. Now let us consider these 5 integers 1, 2, 3, 4, 5. So among these 5 integers which are less than 6, only 1 and 5, their GCD with 6 will be equal to 1. Why? Because the GCD of 2 with 6 will be equal to the GCD, that is the greatest common divisor of 3 and 6 will be 3. The greatest common divisor of 4 and 6 also equal to 2. So therefore they are not relatively prime to 6. This 2, 3 and 4 except 1 and 5. So therefore we have phi of 6, that is the number of positive integers that are relatively prime to 6 will be equal to 2, that is 1 and 5. I hope it is clear to you what is meant by phi function. Now there is a theorem, this one I'll discuss it later on. First let me prove this corollary to this. I'll just assume this result while proving this corollary. This theorem, it states that phi mn is equal to m into n if GCD of mn is equal to 1, means that phi is a multiplicative function. So the proof is not directly as the way we have proved in the case of those Mobius, how to prove Mobius arithmetic function, tau function, sigma function to be multiplicative. This one we have to use a definition of reduced residue system, complete residue system, in order to prove that phi mn is a multiplicative function whenever GCD of mn is equal to 1. So for the time being, I'll just leave it, but I'm going to use this. I'll just assume throughout here in this corollary that phi is a multiplicative function. So what is the corollary states here? Let m is greater than 1 and m is equal to product of distinct prime powers p1 to the power e1 into p2 to the power e2 dash dash pt to the power et, where pi's are distinct primes. Then what we have to prove is that phi of m here is equal to this formula p1 to the power e1 minus 1 into p1 minus 1 dash dash pt to the power et minus 1 into pt minus 1. So here by this corollary, by the above theorem here, if phi of m here will be equal to phi of p1 to the power e1, p2 to the power e2 dash dash pt to the power et. And by assuming that by this theorem phi is a multiplicative function, so with p1, p2 dash dash pt are distinct primes, so I can write this as phi of p1 to the power e1, phi of p2 to the power e2 dash dash phi of pt to the power et. So this corollary will be proved once we show that phi of p1, phi of p in general, okay, this p it can take p1, p2, p dash dash p to the power e is equal to p to the power e minus p to the power e minus 1, which is same as p to the power e minus 1. So put p here such that when you multiply this into this gives you p to the power e minus 1. So once we show that this phi of p to the power e is this, then this the corollary will be proved. So if e here is equal to 1, then phi of p by definition is the number of positive integers, say k, such that k here is greater than equal to 1, less than equal to p, and GCD of k and p must be equal to 1. Okay. Phi of p according to phi of m, it is the number of positive integer less than or equal to p that are relatively prime to p. So phi of p here, if e is equal to 1, phi of p here according to definition, it is the number of positive integers, say k, such that k is greater than equal to 1, less than equal to p, and GCD of k and p is equal to 1. Because if GCD of k and p is equal to, it will be greater than 1 if and only if p divides k. Hence, we have for each k such that k is greater than equal to 1 but less than equal to p, GCD of k and p is equal to 1. We have phi of p here will be equal to p minus 1, because the k greater than equal to 1, less than equal to p, and GCD of k and p is equal to 1. It implies that phi of p will be the number of positive integers less than or equal to p and relatively prime to p, which is equal to p minus 1. So this is the case when e is equal to 1. Now if e is greater than 1, then phi of p to the power e will be the number of integers k such that, again the same thing, k is greater than equal to 1 but less than equal to p to the power e, and GCD of k and p to the power e must be equal to 1. But GCD of k and p to the power e equal greater than 1 is possible only if and only if p divides k. But there are p to the power e, but there are exactly p to the power e minus 1 multiples of p between 1 and p to the power e. Here we have, there are exactly p to the power e minus 1 multiples of p between 1 and p to the power e. So we have phi of p to the power e whose GCD with p to the power e is equal to 1. So we have p to the power e minus p to the power e minus 1 whose GCD with p to the power e is greater than 1. So this will be equal to, so we have phi of p to the power e will be equal to p to the power e minus those p to the power e minus 1 multiples of p between 1 and p, namely this one, p twice p, 3p dash dash, and then p into p, and so on. So among them there will be p to the power e minus 1 into p. So therefore how many of them are there? 1 into p, 1 2 3 dash dash dash, p to the power e minus 1 terms of them which are multiples of p between 1 and p to the power e, such that their GCD with p to the power e is greater than 1. So by removing this, phi of p to the power e will be, we are going to remove, because by phi of p to the power e means it is the number of positive integers less than or equal to p to the power e and whose GCD with p to the power e is equal to 1. So among the multiples of p to the power e, there are p to the power e minus 1 of them, whose means this one, all this, their GCD with p to the power e is greater than 1. So therefore we'll remove all this. So this implies that phi of p to the power e will be p to the power e minus those multiples of p between 1 and p to the power e. And how many of them are there? They are p to the power e minus 1. So we have p to the power e minus p to the power e minus 1, which can be written as, by taking p to the power e minus 1 common, we have p here minus 1. So this complete the proof once, because therefore this is for p. So phi of pm, which is equal to phi of p1 to the power e1 dash dash phi of pt to the power et will be equal, phi of p here will be p to the power p1 to the power e1 minus 1 into p1 minus 1 dash dash phi of pt will be pt to the power et minus 1 into pt minus 1. So this complete the proof of the corollary, that is, if m is greater than 1 and m is a product of t distinct primes, then phi of m is equal to this one, p1 to the power e1 minus 1 dash dash, and so on.